There are many different organic reactions, but for the reactions that we're going to be studying in this course, I've summarised them into 4 categories. So they are proton transfer reactions, second class are addition, elimination and substitution reactions. There are redox reactions, so involving an oxidation and a reduction, and the fourth type are condensation and hydrolysis reactions. So we'll go through each of these. So proton transfer reactions include those of acids and bases. So a strong acid such as hydrochloric acid, when dissolved in water, will completely ionise into hydrogen ions and chloride ions. Whereas a weak acid does not completely ionise, so we get an equilibrium between the weak acid, HF, and its ionised form, so the hydrogen ion and the fluoride ion. Another example of a weak acid is a carboxylic acid. So a carboxylic acid is in equilibrium with hydrogen ions and the carboxylate ion. So these are proton transfer reactions. So donating a proton or gaining a proton, and the reverse reactions there. A base can accept a proton. So ammonia is an example of a weak base. It's able to accept a proton. So when it does, it forms the ammonium ion. And again, this is a reversible reaction. All amines are weak bases. So amines are the bases of the organic world. So any amine is able to accept a proton to form the ammonium ion. Alcohols are also able to participate in proton transfer reactions. So alcohols can accept a proton, so a strong acid, so we've got here sulfuric acid, can donate a proton. The alcohol can accept a proton and form the alconium ion, so a positive charge there on the oxygen. Or an alcohol can donate a hydrogen ion, so that hydrogen can be removed by treatment with sodium metal to form the alkoxide ion. So here we have a negative charge on the oxygen. So the other products are sodium ions and hydrogen gas. The next class of reactions are addition reactions. So this is addition to either a double bond or a triple bond. So we have here, this is ethene reacting with chlorine. One chlorine atom adds to either carbon of the double bond, so that then forms a single bond there between the two carbons. So we go from having a double bond to a single bond. So the same process can occur from a triple bond to a double bond. We can have asymmetric addition. So here we have an asymmetric alkene. So on one carbon there are 2 methyl groups, on the other carbon there are 2 hydrogens, and then we have addition of HCl. There are 2 possible ways this could occur, but there's one major product of this reaction. And so this occurs via Markovnikov's rule, which tells us that the rich get richer. So for this one here, the hydrogen goes to the carbon which contains the most hydrogens. So this one here has 2 hydrogens, it gets the hydrogen, so it becomes a CH3, and then the other carbon will pick up the chlorine, and so that will be the way it goes. So that is the major product there. That's Markovnikov addition to a double bond. The reverse of addition is elimination. So this is where we go from single bonds to forming a double bond, or from double bond to a triple bond. So HBr is eliminated and we form a carbon-carbon double bond. So the bromine from one carbon and the hydrogen from a hydrogen from an adjacent carbon, and then they form a carbon-carbon double bond. Substitution reactions are where one group is substituted for another. So here we have bromomethane, and it is attacked by this hydroxide ion. So the negative charge there of the OH group is attracted to the delta positive charge of the carbon, so it attacks there, and then the bromide ion leaves, and so we've got substitution then. So the hydroxyl group is now attached to the carbon. The bromide ions are the other product. And the next class then are redox reactions. So this is where one species is oxidized and another one is reduced. So for organic compounds, I find it easier to think of these in terms of bonds to oxygen and to hydrogen. So oxidation is forming more bonds to oxygen or fewer bonds to hydrogen. Reduction is the reverse, so it's more bonds to hydrogen or fewer bonds to oxygen. We'll go through some examples. So a primary alcohol, it's primary because there is only one R group attached to the carbon. So this can get oxidized to the aldehyde, and then that aldehyde can be further oxidized to the carboxylic acid. So you can see here, I'm getting, as we go from left to right, so more bonds to oxygen, so one bond, two bonds, and then this one 3 bonds to oxygen, and also fewer bonds to hydrogen. So this carbon has 2 bonds to hydrogen, 1 bond to hydrogen, and no bonds to hydrogen. So the reverse reactions are reduction reactions. From a carboxylic acid to an aldehyde to a primary alcohol are reduction reactions. A secondary alcohol can get oxidized to a ketone. So a secondary alcohol has 2 R groups, and so it get oxidized, so a ketone then is the product. Ketone can be reduced to a secondary alcohol. A tertiary alcohol cannot be oxidized. In biological systems, redox reactions are really important. There are 2 electron carriers that have an oxidized and reduced form. So NADH is the reduced form, can be oxidized to NAD+. NAD+ can be reduced to NADH. The second one, FADH2, is the reduced form, can be oxidized to FAD. FAD can be reduced to FADH2. And the final category are condensation and hydrolysis reactions. So an ester can be formed through the reaction of a carboxylic acid and an alcohol. So under acidic conditions, this will form an ester plus water. So this is a condensation reaction from left to right. The reverse of this is a hydrolysis reaction, where the ester is hydrolyzed with water to form a carboxylic acid and an alcohol. Under basic conditions, the ester can be hydrolyzed, so for example with sodium hydroxide. So rather than getting a carboxylic acid, under basic conditions the product is the sodium carboxylate ion. So this is the conjugate base of the carboxylic acid. So the other product then being an alcohol. Amides can be formed through the reaction of a carboxylic acid and an amine. So when they are reacted together and heated up, they can form an amide and water. So that's a condensation reaction. Carboxylic acid plus an amine to give an amide plus water. An amide can be hydrolyzed under either acidic or basic conditions. So an amide plus water plus acid will give carboxylic acid and the ammonium salt. Under basic conditions, the amide is hydrolyzed to give the carboxylate ion and the amine. So note the different forms there of the carboxylic acid and the amine under either acidic or basic conditions. So under acidic conditions, it's the carboxylic acid. Under basic conditions, it's the carboxylate ion. Under acidic conditions, we have the ammonium ion, so positive charge on the nitrogen, whereas under basic conditions, it is the amine. And another example of a condensation reaction is a glycosylation reaction between 2 monosaccharides, so forming a glycosidic linkage. So here we have 2 glucose molecules that will then form a glycosidic linkage. So this is an alpha 1,4 linkage between these 2 glucose monosaccharides to form a disaccharide, which is named maltose. The reverse reaction is then the hydrolysis of this glycosidic linkage. So the disaccharide will be hydrolyzed under acidic conditions and generally with the assistance of an enzyme to form the 2 monosaccharides.